All right, today we're going to see some examples of something called a telescoping sum, and the name just comes from what happens when we solve these. So we're going to start by evaluating the sum that's given below, and we're going to add all of the terms of this particular sequence or of the result of plugging in this function when we plug in a 0, and then we plug in a 1, and then we plug in a 2, and so on until we stop at n. And again, n is not necessarily a number that we know the value of, but it is an integer, so we're going to stop at n. So let's just see what happens as we begin this process by actually plugging in numbers. So we're going to start by plugging in a 0. So that's going to be 1 over 0 plus 1 minus 1 over 0 plus 2. And that's going to become 1 over 1 minus 1/2, right? And so I'm going to stop plugging in the 0 and just start writing the terms that we end up with. But when we plug in a 0, we end up with that. Okay? So then the next term is going to be what happens when we plug in a 1. All right, so when we plug in a 1, that first fraction is going to be 1/2, and that second fraction is going to be a third. And when we plug in a 2, first fraction is going to be a third, second fraction is going to be a fourth. All right, and this is going to continue. And I'd challenge you to figure out what the solution is here as this continues. It goes on and on and on and on till eventually we're adding, I would say, 1 over n minus 1 over n plus 1. And then finally, if I plugged in n, I would get n plus 1 minus 1 over n plus 2, right? So this is where it stops. And so what does this eventually equal? Well, something cool is going to happen to each of these terms, because you'll notice we can drop all of these parentheses because there's a plus sign outside of all of them. So imagine I distribute a positive 1. Nothing's going to change. So I'm just going to knock out each of those sets of parentheses and help us see what is going on here a little bit easier. Okay. So with these gone, you might be able to notice that there's some nice cancellation that's going to take place. Because you'll see, if I've got a negative 1/2 here and a positive 1/2 here, those two things are going to cancel. Negative 1/2 plus 1/2 is 0. And I'm going to have a similar situation with this negative 1/3 and a positive 1/3, and a negative 1/4 and a positive 1/4. And this is going to cancel with what will inevitably be a positive 1/5, and this will continue over and over and over. There would have been a negative 1 over n here if I had been continuing this process, and that would cancel with this 1 over n. These two terms cancel. This is not going to cancel with anything, though. The negative 1 over n plus 2 and the original 1 are not going to go away. So with this pattern, you see that everything actually cancels in the end except the 1 and the 1 over n plus 2. And so what looked like it was going to be sort of a challenging sum to evaluate turned out not to be, and you're going to see this pattern sort of arise in a lot of the examples we're going to do, where you'll see a lot of cancellation as long as you sort of plug in numbers that you know to maybe get a visualization of what that pattern is in the first place. All right, let's do one more example. Okay, so we're asked to find now the limit as n approaches infinity of this sum. So again, we don't know where to stop adding, right? I'm going to plug in a 1 and then a 2 and then a 3 and then a 4 all the way up to whatever n is. And we're going to keep pushing that n towards infinity and see what happens to this sum. So it's possible that this will just keep getting larger and larger and larger and it'll approach infinity. But it's also possible that this is going to telescope down to some particular value or some particular expression that'll be a little bit simpler to work with. So we're going to do some algebra here just to make this look a little nicer for us. I would recommend distributing this exponent 2 inside of that fraction there first. All right, so the next thing I can do is take this 3 over n and distribute it inside of what we have in our parentheses there. So we'll call this the limit as n approaches infinity of the sum of all terms when I is 1 through n of 3i squared over n cubed plus 3 over n. And I could leave the I squared out or in, but remember, right now, I want to recognize that that I is the variable here, and n is a number. I don't know what that number is, but it is a value. It's a constant value. So a way to better write this maybe would be to leave it as 3 over n cubed times I squared. Because I do want to get to a point where I'm recognizing that the I is the variable here and the n is not. And what I can do at this point is use one of my theorems that says if I'm taking the sum of a sum, then I can take the sum of the first element and add it to the sum of the second element. And I could do that just by leaving the limit outside. So I have the limit as n approaches infinity of, and I'll use a square bracket just to show that this is a pretty large component. So the sum from when I is 1 through n of 3 over n cubed times I squared plus the sum from when I is 1 through n of 3 over n. And I'm going to attempt to use some of those theorems from yesterday to make these things easy to work with. And remember that I is the variable here. Everything else is a constant. So n does represent a value. We just don't necessarily know what that value is. But remember, we're plugging in all the integers from 1 to n. So n must be something. Okay, so we're going to treat it like a constant, and we're going to use the theorem that allows us to remove the constant from the sum. So the limit as n approaches infinity of, I'm going to take my constant out and leave the sum from I is 1 through n of I squared plus, and I'm taking this constant out as well. So 3 over n comes out, and I have the sum from 1 through n of 1. And one of those is going to be pretty easy to deal with. The other one we can deal with too because we have some theorems that help us do this. So again, I haven't really even touched that limit yet. I'm going to try to deal with that limit last. So I have the limit as n approaches infinity of, and we have 3 over n cubed. We also know what this limit, or what this sum is going to converge to. We know what this equals. One of our theorem tells us how to evaluate the limit as, or the sum from 1 through n of I squared. And so we can use that theorem to just, or hopefully recall, that this is equivalent to n times n plus 1 times 2n plus 1 over 6. That's this. Okay, plus 3 over n, and we also know that the sum of all the terms from when I is 1 through n of 1 is n. That's another one of our theorems from yesterday. So we're using those theorems to create situations we're familiar with so that those sigmas disappear from this equation because I know what these things are equivalent to, right? And I know that this is equal to just n. Okay, so now I can algebraically sort of push those things together, which I'll do now. Okay, so a couple things to point out here. 3/6 is the same as 1/2. That's why you see that reduction there. And over here we've got n divided by n, so that 3 is left behind. So what I'm going to do with this middle expression, that big fraction we have, is I'm going to separate that into a lot of different components. So I'm going to get the 1/2 out of there. All right, so 1/2 is its own times, and again, I'm not introducing anything new, I'm just rewriting this. I'm going to pull the n that's all by itself out and divide that by one of these n's. Okay, I'm going to divide the n plus 1 term by one of those n's, and I'm going to divide the 2n plus 1 by one of those n's, and I do still have this plus 3 out here. And so this is sort of going to remind you of what we did when we had indeterminate limits. We're trying to separate these fractions, and we're going to continue to do that within these fractions here, but with addition. Okay, so what's going to happen with a couple of these is this fraction is going to work out pretty nicely. So my next step, I'll rewrite this as the limit as n approaches infinity of 1/2 times 1, right, because n divided by n is 1, times, and if I separate this fraction into two fractions, then I'm going to have n divided by n plus 1 divided by n times, I can do the same thing over here, and I'll have a 2n divided by n plus a 1 divided by n plus 3. So you're just starting to see some tools and some tricks that might be useful to simplifying some of these. All right, so now we're going to see some nice things happen with these terms here. Those ends will cancel and those ends will cancel. All right, so let me just rewrite what this is going to look like once I've done that cancellation and sort of tightened this all up. All right, so 1/2 is here because 1/2 times 1 is just 1/2. These cancel to be a 1, this cancels, we have a 2. And now we can actually evaluate this limit pretty nicely because you're going to see that as n approaches infinity, if this is going to infinity, then this whole term is going to go to 0, right? If that denominator is growing, then that whole term is going to 0. Same thing with this term, that's all going to go to 0 if n approaches infinity. So if n is approaching infinity, then this entire expression is going to end up being 1/2 times 1 plus 0 times 2 plus 0 plus 3, which we can simplify 1/2 times 1 times 2 plus 3, and 1/2 times 1 times 2 is 1, which plus 3 is 4. Not what you would have expected. So originally this expression looked like a mess, but it sort of telescoped down to become a pretty nice number just because of the way that this sequence works out and the way that you can apply some of those sum theorems to help you deal with this summation that's in sigma notation. All right, so a couple examples for you to look through. Continue to work on the homework set that's due tomorrow night.